Good morning, students. Write your name and seat number in the chat box. Yesterday, we started this chapter, Solutions. So this is having the weightage 4 marks with option 6 marks, and the introduction part is already completed. This is a physical chemistry chapter, and one numerical one numerical will be expected from this chapter. It will be for 1 mark or 2 mark, or it will be for 3 marks. So yesterday at 11 o'clock, I sent the PDF file, the notes of this chapter to you. So I think many students replied. So today, please reply me. So just I will take a quick revision. What is mean by solution, what is solute and solvent. You know these terms already, we studied in the school days also. Solutions, it is a homogeneous mixture. It is in one phase. Homogeneous means it is a one phase mixture of the two or more substances. Generally, the solution is prepared with solute and solvent. But before this, one picture is created in your mind that a solution is always contains solid, solute, and the solvent is liquid. But it is not true. Solute and solvent can be solid, liquid, or gases, and depending upon this types of solute solvents, there are 9 types of solutions are there. We yesterday explained. I yesterday explained this types of solutions: solid, 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 liquid, solid gas. So today, go through this. I have already sent the notes of this chapter in detail to you. And I also told you one mark question will be there on this chart. Then what is mean by saturated solution, unsaturated solution, and supersaturated solution? That these definitions can be asked for the examination, remember. Saturated means they contains maximum amount of solute dissolved in a given amount of solvent. Unsaturated means we can dissolve more solute till the saturated solution can be obtained, and supersaturated solution means it contains extreme amount of solute, means if the little amount of solute it is added, it can be precipitated. So this is completed. Then solubility, it is nothing but the amount of solute dissolved in a solvent at specific temperature. It is measured in moles per liter, remember. So this unit is very important. And these factors affecting on solubility, there are 3 factors: nature of solute and solvent. Remember, like dissolves, like polar solute dissolved in polar solvent, and non-polar solutes dissolved in non-polar solvent. Then effect of temperature and solubility. Actually, there is a no effect. Actually, the fact direct, there is no correlation between solubility and exothermicity and endothermicity. Some solute solubility increases, or some solute solubility decreases when the temperature is increased. So there is no direct correlation between temperature and solubility. But generally, solubility increases when temperature is increased. But this is not always true. Some solutes like this calcium chloride, its solubility, when it is dissolved in water, actually the heat is released. So it is expected its solubility should decrease when increase in temperature, but it is not true. Calcium chloride, when it is dissolved in water, its solubility also increases. And the next factor is solubility of the gases. It is generally decreases, because you know, when the temperature is increased with the vapors, uh, with the vapors of the liquid, the gases are also comes out. So 100% the solubility will be less. And the good example of this is aquatic fish, like or aquatic. In case of summer days, the fish prefers to stay at lower side of the pond, because In the upper side, the dissolved oxygen will be evolved. This is a good example of solubility of gases. It is decreases and with increase in temperature. And this is effect of pressure on solubility. When the pressure increases, solubility increases. Good example is beverages bottle. When the cap is removed, the effervescence comes out. The effervescence comes out means dissolved carbon dioxide, it comes out. When the solubility is more, remember, when the pressure is increased, the solubility will be increased. This is given by the very famous scientist Henry's law. So according to this Henry's law, what is this? S is directly proportional to P, increases solubility of the gas in liquid is directly proportional to the P. This is the KH is Henry's law constant. So S is equal to KHP. And the units are also very important. The unit of this KH is equal to S divided by P. So S is solubility. It is measured in moles per liter and the pressure is in bar. So the unit will be moles per liter per bar. This is the unit of Henry's law constant. And also I discussed this example with you when why effervescence comes out, because carbon dioxide is the mixture of carbon dioxide and air is filled in the carbonated waters. I also explained this example yesterday, and this example you can solve at your home. I want to start the next part. This is exceptions to the Henry's law. This part is a non-evaluative part. This is deleted due to the COVID-19. So no any question will be asked on these exceptions to the Henry's law. It is very simple actually. These two gases, ammonia and carbon dioxide, they do not obey Henry's law because these gases reacts with water, and this shows exception to the Henry's law. What is Henry's law? Solubility of the gas, it is increases with pressure, but this is not true in these two types of gases. So this is not for your examination. Now this part is very important for the examination. We will start from this vapor pressure of solutions of liquids in liquids. So here solute is a liquid and solvent is also liquid, and I will explain this concept vapor pressure. So vapor pressure, it is nothing but the pressure of the vapor on the surface of the liquid. I will explain with this diagram. See, this diagram is not included in your textbook also. So in this diagram we can see it is a solvent in open container because it is not closed. We can see here the molecules are coming out when it is heated, or if the volatile solvent is kept here, it will be evaporated. So when it is not closed, what will happen? The particles of the vapors, it will comes out undergoing evaporation. But in the second figure, it is in the B figure, we can see clearly this is a liquid is kept in the container, and this container is closed with a cork. And what is happening? Say, as the solvent is volatile, the vapors are coming out. The vapors are coming out. The vapors will collide here and there. But as the container is closed, again condensation will be started. So these are the vapors, and these vapors creates a pressure on the surface of the liquid. This is called as vapor pressure, remember. And in the vapor phase, we can see here vapors also, and the water also, because at the condensation the water is also coming down, because when these vapors strikes on the cork, the condensation will be started. So evaporation and condensation process will take place here. So in this diagram, clearly we can see in the vapor phase, we can see vapors are also there and liquid is also there. So again, I am coming back to this explanation. When a solution of two volatile liquids A1 and A2 is placed in a closed container, and both the liquids are vaporized. So in this container, A1 and A2 two liquids are mixed and let them vaporize. So what will happen finally an equilibrium is established between vapor and liquid phases. Means this evaporation will be stopped at one stage. There will be equilibrium will be present, and vaporization means evaporation and condensation. This process will be stopped at equilibrium. So both the components are present in the vapor phase. Both the components means vapors are also present and liquid is also present in the vapor phase. Actually, this relation is given by one scientist, Raoult's law. This is the name of the scientist. This relation, which relation? The relation between the partial pressure of the components and their mole fractions. Mole fraction in 11th standard we studied about this. Mole fraction means the number of solutes. So this relation between partial pressure and mole fraction is given by the scientist Raoult's, and this is included as a Raoult's law. So this Raoult's law is asked for examination for 2 marks. No any question will be asked on this vapor pressure, remember. So we must know what is meant by vapor pressure. So in simple words, vapor pressure is nothing but the pressure of the vapors on the surface of the liquid. At equilibrium, the condensation and evaporation will be at equilibrium, condensation and evaporation will be stopped. Means the evaporation will be stopped at equilibrium. So what is this Raoult's law? Very important for the examination. Very important for 2 marks. Because in this chapter solution, there are 3 laws. Raoult's law is there, Henry's law is there, and another Raoult's law for non-volatile solute is there. So out of these 3 laws, 1 law will be asked for examination for. First, I will give the statement. Means what is the conclusion of this Raoult's law? क्या बोलता है Raoult's law? See, it states that the partial vapor pressure of any volatile component. See, this word is introduced, newly introduced, partial vapor pressure or vapor pressure. Forget about this word partial. So what is this Raoult's law? It states that the partial vapor pressure of any volatile component of a solution, means if if any volatile component is present in the solution, it is equal to, means partial vapor pressure is equal to the vapor pressure of pure component multiplied by its mole fraction in the solution. So I request all the students, don't I request you ratta मार के इसको मत पढ़ो. I will give one statement. I will give one example. So with this example, we can remember this law. Don't memorize or पाठ करू नका असं मी म्हणतो. Consider a binary solution. So binary solution means binary. This word indicates it is a mixture of 2 solutions. Binary. Remember, consider a binary solution of 2 volatile liquids A1 and A2. So a solution contains A1 and A2 and both are volatile. So P1 and P2, these are the vapor pressures or partial vapor pressures, and X1 and X2, these are the mole fractions of the solution. Once again, I am explaining. We are taking the binary solution. Binary solution, it is a solution of 2 liquids mixed with each other. And these are the liquids A1 and A2. P1 and P2, these are the vapor pressures. P1 is the vapor pressure of A1 and P2 is the vapor pressure of A2. And X1 is the mole fraction of A1 and X2 is the mole fraction of A2. Now, according to this Raoult's law, again I am coming. So Raoult's law states that partial vapor pressure of any volatile component in of a solution is equal to the vapor pressure of pure component multiplied by its mole fraction. So this, according to the Raoult's law, I am coming from this statement. From this statement, we can write P1. So what is P1? I am coming to P1 and P2. These are the partial vapor pressures of A1 and A2. So this P1 is equal to P01 into X1. This is according to Raoult's law. So by remembering this equation only, we can write the statement. So from this statement, I am preparing the, from this equation, I will prepare the Raoult's law again. So P1 is what? P1 is the partial vapor pressure of any volatile component. So the P1 is the vapor pressure of volatile component A1, and P2 is the vapor pressure of volatile component O2, A2, because A1 and A2 both are volatile. So P1 is equal to P01 into X1. Here P01 and P02 are the vapor pressure of pure liquids A1 and A2. So, and this P1 and P2, these are the vapor pressures of A1 and A2. So again, I'm coming to the statement. According to Raoult's law, say P1 and A2, P2, these are the partial vapor pressures, and X1 and X2, these are the mole fractions of the solution. So according to the Raoult's law, again I'm coming this P1 and P2. P1 is equal to P01 into X1. Here P1 is the partial vapor pressures of A1, and P01 and P02, these are the pure liquids. See, P01 and P02, these are the vapor pressure of pure liquids A1 and A2 respectively. So this statement is obeyed here. This statement, again I am coming to this statement because many students didn't understand what is this Raoult's law. So Raoult's law is nothing but the partial vapor pressure of any volatile component, it may be A1 or it may be A2, is equal to the vapor pressure of that component. Means P01 indicates it is the vapor pressure of the pure component of this P1, and X1, this is the mole fraction of the component A1, and P2 is the vapor pressure of the component of that component A2, and P02 is the vapor pressure of pure component. Why I am using this pure component word? Because if any non-volatile solute is dissolved in it, the vapor pressure is not equal to that non-volatile component, remember. So don't get confused. Again and again I am using this word pure component. So only the vapor pressure is related to the pure component and the mole fraction. So by using this equation, this P1 or P2, we can remember the Raoult's law. So what is the Dalton's law of partial pressures? Means Dalton's already given in 11th standard, we learn about this Dalton law. According to the Dalton's law, the total pressure P or P total, it is denoted with P or P total in the above solution is equal to P1 plus P2. So P is equal to P1 plus P2. We are combining these P1 and P2. P1 already P01 into X1 plus P02 into X2. It is equation number 2.3. But in 11th standard, we learned about this mole fraction, X1 and X2. X1 plus X2 is equal to 1. So what is this X1 and X2? These are the mole fractions. X1 is a mole fraction of uh, any component of solute or solvent, and X2 same. It may be the mole fraction of solute or solvent. So always this total is always 1. Remember, X1 plus X2 is always 1. So if X1 plus X2 is equal to 1, X1 is equal to 1 minus X2. X1 is equal to 1 minus X2. This value we have to put in this equation. So we are going to put the value of X2 is equal to, X1 is equal to 1 minus X2. So again, P is equal to P01. Here in this equation, we are going to put this value P0 P naught 1 x1 plus P naught 2 x2. So 1 minus x2, we are putting the value of x1 in this equation. So P naught 1 in bracket, this value is put here, 1 minus x2, so P naught 2 into x2. P naught 2, we are not making any change of this P naught 2 into x2. So by multiplying this P naught 1 into 1 minus x2, P naught 1 into 1, it is P naught 1 minus P naught 1 into x2, it is right, it is written here, see, plus P naught 2 into x2 as it is. After solving this equation, we get this P is equal to P naught 1 plus P naught 2 minus P naught 1 into x2. x2 को common हमने निकाला है, and by rearranging this equation, P naught 1 plus P naught 2 minus P naught 1 into x2. This is equation number 2.4. Remember, this is equation of Raoult's law. So according to following conclusions can be drawn from this equation. The total vapor pressure, this is the P is indicate the total vapor pressure of the solution, and this it is related to the mole fraction of any one component. Any one component means it may be related to the solute or it may be related to the solvent, any one component. So total vapor pressure of the solution can be related. This is not actually important for your examination. By using this statement, we can draw the conclusions. This P is related to the mole fraction of any component, or the total vapor pressure of the solution varies linearly with the mole fraction. This is actually not important. Directly I am coming to the graphs. These graphs are also not asked for the examination, but you should know what is these graphs. So if we can see, this is a graph of vapor pressure and mole fraction is given here. Actually, there are two graphs. This is one graph like this one, and this is a second graph. Two graphs are mixed together. This is a vapor pressure on this axis, and y-axis, and this is mole fraction. Mole fraction, there are two components, x1 and x2. So first here, for P naught 1, there are three graphs I will explain. First one is P1 is equal to P naught 1 x1. The plot of P1 versus x1 is a straight line 1, this one. See this line 1 indicates here the plot of P1 versus x1. This is a P1 and this is a x1. So the graph of partial pressure P1 with the mole fraction x1 is a straight line 1 with, if P1 is equal to 0 at x1 is equal to 0, if P1 is 0 at x1 is 0, and P1 is equal to P naught 1 and x1 is equal to 1. So here we can see P naught to P1 is equal to P naught 1. This is a graph of P1 versus x1. P1 versus x1. See here x1 is equal to 1. And this graph is actually wrongly plotted in your textbook. Make a correction. X1 is 1 here and x1 is 0 here. See, but in your textbook there is a printing mistake. I corrected this diagram here. So also we have to make the correction in your textbook with this diagram. This there are three graphs. Graph number, this is a line number 1, this is a line number 2, and this is a line number 3. Line number 3 indicates it is a total pressure. With this statement, we can understand the dashed lines 1 and 2 represents the partial pressure of the component. So this is a line of P1 x1, this is a line of P2 x2, and this is a line of total pressure P. This is line of total pressure P. This is not actually asked for the examination, but for understanding concept, how this partial pressure is related to the mole fraction. These three graphs indicates the relation between partial pressure and these graphs are the Raoult's law graphs. If for the examination only this statement will be asked for you for 2 marks, we don't require to draw these graphs. So graph 1 is when P1 is equal to P01 and X1 is equal to 1. In the second graph, P2 is equal to P0 to X2. This graph is P2 versus X2. So this one is P2 versus X2. See, means at this 0 and this is 1. And if this graph is considered, if this plot is considered, P1 and X1, here is 0, X1 is 0, and here is 1. So in the second graph, we can see clearly it is also the straight line P02 versus X2. This is P02 and see this is P02 and X2. P01 X1, P02 X2. See, X2 is 1 here, X1 is 1. This one at this side. And third graph is P is equal to P01 plus actually P is equal to P01 plus P02. This in this straight line, we can see clearly P is equal to P01, X2 is equal to 0, and P is equal to P02, and X2 is equal to 1. We can get this line. So I am not going in detail with these graphs. Now this is a very important for 1 mark, ideal and non-ideal solution. What is mean by ideal solution and what is mean by non-ideal solution? This may be asked for 1 mark. So what is ideal solution? I will explain. So ideal solutions are the solutions which do not obey the Raoult's law. Remember, ideal solutions means, which obeys Raoult's law, and non-ideal solutions are the solutions which do not obey Raoult's law. But the ideal solutions are the solutions which obeys the Raoult's law. And you know what is Raoult's law? Just I explained the Raoult's law. No heat is evolved or absorbed when two components forming the ideal solution, when these are mixed together, the enthalpy of mixing is 0. This is a delta H mixing. Delta H mixing is equal to 0. This indicates means no heat is evolved or no heat is absorbed when these two components are mixed together. So these are the some statements by which we can identify which is ideal solution and which is non-ideal solution. When delta H of the mixing is 0, it is ideal solution. When the solution obeys Raoult's law, it is ideal solution. And third statement is there is no volume change. Means volume cannot be changed when the two components forming an ideal solution and when these are mixed. So delta V of the mixture is also 0. Delta H of the mixture is also 0. So these are the some hints to identify the ideal solution. Means volume of the ideal solution is equal to the sum of volumes of the two components. Two components taken for a mixing. Then number 4 statement is an ideal, in case of an ideal solution, solvent solute, solute solute, and solvent solvent molecular interactions are comparable. Means these interactions are quite comparable. And last one, the vapor pressure of ideal solution is always, remember this is a very important, the vapor pressure of ideal solution is always lies between vapor pressure of pure components as shown in graph. I will show the graph. It is important to understand that perfectly ideal solutions are uncommon. Perfectly means the ideal solution which obeys all these conditions, it is uncommon, and the solution such as benzene plus toluene behaves nearly ideal, but it is also not ideal. The mixture of benzene and toluene behaves nearly ideal. So for the examination purpose, they may ask, write one example of ideal solution. We can write this example. Benzene plus toluene means this mixture benzene plus toluene obeys these all conditions. This obeys Raoult's law. The delta H mixing is also 0. Delta V mixture is also 0. The interactions of solute-solute, solute-solvent, these are comparable. And also the vapor pressure of ideal solution always lies between the vapor pressure of pure components. Opposite to this one, there are non-ideal solutions. These are completely opposite to the non-ideal solutions, means these do not obey Raoult's law. Then second one, vapor pressure of these solutions. See, this vapor pressure of the solutions can be higher or lower than those of pure components. But in case of ideal solution, we can see here the vapor pressure always lies between vapor pressure of pure components. But in case of non-ideal solution, the vapor pressures can be higher or lower. They cannot lies between vapor pressure of the pure components. This is a main change. So the interactions also greater or less than the magnitude. The interaction of solute-solvent interactions either greater or less than the magnitude of solute and solvent interactions. There are two deviations from this Raoult's law. Means non-ideal solution shows two types of deviations from Raoult's law. One is a positive deviation and one is negative deviation. We can see in this graph also. I will explain. This graph is a positive deviation and this graph is negative deviation. Deviation means it is nothing but the graph of vapor pressure and mole fraction again. This vapor pressure and mole fraction. These graphs are similar to the Raoult's law. So first I will explain what is this positive deviation from the Raoult's law. Side by side I will take the help of the graph. Positive deviations are exhibited by the solutions in which solute-solvent intermolecular attractions are weaker than those between solute-solute molecules and solvent-solvent molecules. So these positive deviations can be expected by the solutions in which these interactions, molecular interactions, solute and solver interactions are attractions are weaker. Which attraction? Solute solvent intermolecular interactions are weaker than these two interactions, solute and solvent interaction. And then the second thing, the vapor pressure of such solutions are higher than those of pure components. As shown in figure, we can see in this figure, we can see this vapor pressure. See this vapor pressure. So this vapor pressure of such solutions are higher than those of pure component. This is a graph of a green line. We can clearly indicate this is a pure component. This is a pure component. This already explained in Raoult's law. This blue colored lines, these are the deviations shown by positive deviations. These are the vapor pressure of the solutions. Positive deviation. We can see clearly the vapor pressure of the solution is higher. And here in case of negative deviation, we can see this graph, vapor pressure of this solution is lower than the vapor pressure of the pure component. Here vapor pressure, see this blue line indicates the vapor pressure of this solutions. It is more than the vapor pressure of the pure component. We can see here. So the examples, positive deviations and negative deviations. See the examples of positive deviation first. Examples are the solutions of ethanol, acetone, then carbon disulfide and acetone. These shows positive deviations from the Raoult's law. So these are the positive deviations and these are the negative deviations are exactly opposite. We can see these diagrams are totally opposite. So negative deviations from the Raoult's law, I will explain. This is exactly opposite. The negative deviations are exhibited by the solutions in which these interactions are stronger. Which interaction? solute solvent interactions, intermolecular interactions, attractions are stronger. But in case of positive deviations, we can see solute solvent intermolecular attractions are weaker. And in this, solute solvent interactions are stronger than the solute solute and solvent solvent interaction. The vapor pressure is also, the vapor pressure of such solutions is lower. See, in this diagram, we can see the vapor pressure of these solutions are lower than this is a vapor pressure of the pure component. It is shown in this figure number B. So figure B is negative deviation from Raoult's law, and this figure A is positive deviations of Raoult's law. Example are given: phenol, aniline, chloroform, acetone. This shows negative deviations of the Raoult's law. This may be asked for 1 mark, or it is graphs are not expected from the students, remember. So don't take too much tensions about these graphs. Graphs are not expected, but this is expected. Negative deviations means what, and what is mean by positive deviations. Now I'm coming to the next part, is a colligative property. Just I will introduce what is mean by colligative property. So solutions part is completed. This chapter is divided in 2 parts: solutions and colligative property. So in solutions, we studied what is mean by solute, solvent, different types of solutions. What is saturated solution, supersaturated solution, unsaturated solution. Then what is factors affecting on solubility. There are 3 factors: solutes, nature of solute and nature of solvent, then effect of temperature, effect of pressure, then Henry's law, then Raoult's law. Vapor pressure, new concept is introduced. So Raoult's law is also completed. Then there is a positive deviations of Raoult's law, negative deviations of Raoult's law. And then the next part of this chapter is colligative properties. Colligative, it is actually the Greek word colligative means collective properties. So these are the collective properties of the solutions, depend upon the number of solute particles, remember. This is asked for 1 mark for the board exam. Colligative properties depend upon the number of solute particles, means the number is important here. Nature of that particle is not important. The number of solute particles are important, and their natures is least important or not important. They will confuse, they will give the option. The colligative properties depend upon ... They will give the nature, they will give the number, or they will give another confusing options. So remember this thing, all the colligative, this is a Greek word, means collective properties of solute particles. This depends upon the number of solute. Number is important here. Number of solute particles, and nature is not important. So there are 4 colligative properties included in this chapter. Number 1 is vapor pressure lowering, or it is also called as lowering of vapor pressure, means vapor pressure kami ka hoto te, number 1. Number 2, boiling point elevation, means elevation indicates increase in boiling point. Why this boiling point increases? Then depression in freezing point, why the freezing point decreases, and osmotic pressure. So after these 4 colligative properties, this chapter will be completed. So I will explain this vapor pressure lowering, and I will stop here. Before this vapor pressure lowering, we are familiar with this word vapor pressure. Vapor pressure, it is nothing but the pressure of